Linear and absolute value inequalities. Our objectives: use interval notation to express inequalities, use properties of inequalities, solve compound inequalities, and solve absolute value inequalities. Solving linear inequalities. Now here is a true inequality. -2 is less than 5. What if we multiply by a -1? We get 2 is less than -5. We've changed that to a false statement. So let's start again with -2 is less than 5. If we multiply by -1, we should get 2 is greater than -5. Notice that the direction of the inequality has been switched. This is because inequalities are a directional statement, and when you negate them, you change the direction of that statement. So, when we multiply, or even if we divide both sides of an inequality by a negative number, you must reverse. So, when you multiply or divide both sides of an inequality by a negative number, you must reverse the direction of the inequality sign. Solve each of the following. Express the solution as an inequality with a graph and in interval notation. 1 is greater than 7 plus 3x. There's a couple of ways you can go about this. If you like, you can make sure that you get your x's on the left side and everything else on the other. So let's head with that strategy. I'm going to subtract 3x from both sides. Now I need to subtract 1 so I don't have a constant on the left side. Here I'm going to divide both sides by -3 so that I am isolating my variable. At that moment, we need to make sure and flip the inequality. X is now less than -2. When we graph this, we can just put the critical value of -2 there, and we are shading all the things that are less than -2. We'll put a parenthesis on the -2 to show that it is not included in the answer set. And in interval notation, we read from the left on the graph, and it's coming from -infinity, and we stop at -2, but don't include -2. So here we have a little bit more complicated problem because we have a set of parentheses. So I'll need to go ahead and distribute through. I get 3x plus 3 plus 7x is less than equal to x plus 12. Just like we did in the last one, let's get our x's on the left side and everything else on the right. For now, I can combine like terms. Then I'll subtract x from both sides. Then I'll subtract 3 from both sides, isolating my variable term. And now I want to completely isolate the variable by dividing by that coefficient of 9. So my answer is x is less than equal to 1. Notice I did not flip the inequality here because I was dividing by a positive number, not a negative number. I'll go ahead and graph 1 on the number line, and x is less than or equal to 1. So I'll shade to the left and put a square bracket on 1. Putting this into interval notation, I read from the left. We're coming from -infinity, and we go until 1 and include the value of 1. Again, we have to distribute through our parentheses. I'll collect my like terms. 4x plus 11 is greater than or equal to 2x plus 9. Let's subtract 2x from both sides. And we'll subtract 11 from both sides. And then divide both sides by 2. And I get x is greater than or equal to -1. And notice here I'm dividing a negative number, but I did not flip the inequality because I'm not dividing by a negative number. It has to be that you're dividing by a negative number to flip the inequality, or multiplying by a negative number. So here we have x is greater than or equal to -1. We'll mark that value on the number line. And x is greater than or equal to, we put our square bracket, and in interval notation, our answer is -1 to positive infinity. Now we'll take a look at solving compound inequalities. A compound inequality includes two inequalities in one statement. A statement such as 4 less than 2 times x minus 4 less than or equal to 10 actually means 4 is less than 2 times x minus 4 and 2 times x minus 4 is less than or equal to 10. You might choose to keep the compound inequality together to solve or separate it. I'll show you both methods here. When I'm looking at the inequality on the left, I've kept this together. Okay, the first thing that I see is I need to go ahead and distribute that 2 through the parentheses, and I'm left with this. Now, if I had just this part of the inequality, what I would do would be adding 8 to both sides. If I had just this part of the inequality, I would be, again, adding 8 to both sides. So what I'll do here is add 8 to all three parts. 4 plus 8 is 12, less than 2x minus 8 plus 8 gives me just 2x, less than equal to 10 plus 8 is 18. Now I'm ready to just divide by 2. Just like we did in the last step, we're going to do this for all three parts of the inequality. So I get 6 is less than x, which is less than equal to 9. So we put our answer into inequality notation. Let's go ahead and put this on the number line so we can picture what our solution looks like. Now, how can x be greater than 6 but less than equal to 9 at the same time? That place would be between these two values. And this strictly less than means that I'm not going to include 6. The less than equal to 9 means I will include the 9. So in interval notation, my interval is -6 to 9, including the 9. Now over here you can see this is the same inequality. It's just been broken into two statements joined with an and. We have the left side here and the right side here. So I'll show you how we solve that way if we want to break it up. I'll go ahead and distribute my 2 through the parentheses, and then I want to go ahead and try and get your x on the left side. So I'm going to subtract 2x. Again, this is just one way to do this. I'm going to subtract 4 from both sides. Now I'm going to divide by -2, and be careful to flip your inequality sign. So this is now x is greater than 6. As we do this, we want to keep our AND statement between the two pieces so that they are still together. I'm going to distribute my 2. 2x minus 8 is less than equal to 10. And 2x is less than equal to 18 by adding 8 to both sides. And I'm going to divide both sides by 2. So I eventually get down to x is less than equal to 9. When we think on the number line, go ahead and put your values there. And think about where on the number line we would be greater than 6 and less than equal to 9 at the same time. These numbers are not going to be greater than 6, so we don't even worry about those. Those are not going to work for us because it has to be true for this statement and for this statement. So let's try the middle. Between 6 and 9, maybe 7. Is 7 greater than 6? Yeah. Is 7 less than equal to 9? Yes. And so will every other number that's between 6 and 9 on that interval. Okay? All of these numbers in here are greater than 6 and less than equal to 9. Let's try over here. Are these numbers greater than 6? Yes. Are these numbers also less than equal to 9? No, they're not. So we go ahead and cap those, making sure we're paying attention to whether we are including the critical value or not. And then we get 6 to 9, including the 9, just the way that we did doing it the other way, where we kept the compound inequality all together in one statement. Solve the following inequality. Express your answer as both an inequality and in interval notation. Here, 3x plus 2 is greater than -25. Well, let's go ahead. Subtract 2 from both sides. Then we'll divide by 3. I get x is greater than 9. And I'm going to add 40 to both sides. And I divide by 5. This gives me x is less than 9. So let's try with this. I have x greater than -9 and less than +9 at the same time. And this is going to be the place where that happens. All of those numbers are greater than -9 and less than +9 at the same time. And we won't include our endpoints here because these are strict inequalities. And in interval notation, we have -9 to 9. You'll notice the directions didn't ask for a graph, but I did one because this is the way that you're going to picture what the solution set is so that you can get it into your interval notation form. Solve the following inequalities. Express your answer in interval notation. This is another compound inequality, except that we have the word or instead of and. So let's go ahead and start. I'm going to subtract 1 from both sides, divide by 3, and I have x is greater than 6. Over here, I'm going to subtract 4 from both sides. Then divide by negative 7, so this gives me an x greater than equal to positive 1. Right, when I graph this so that I can see what the solution set is, we have the following. X is greater than 6, or x is greater than equal to 1. Now what an or means is that as long as we have one or the other, then it's a true statement. So when I'm looking here, are these numbers greater than 6? No. Are they greater than equal to 1? No. It has to be true for at least this or this in order for it to be included in our answer set. How about between 1 and 6? Are these numbers greater than 6? No. Are they greater than equal to 1? Yes. So we can go ahead and include this interval on the set because it's at least true here or here. How about numbers after 6? If we put any number from this interval in, is that number greater than 6? Yes. Is it greater than or equal to 1? Yes. So we have at least one place where those numbers would give you a true statement. It's true here. It's true here as well. We just need at least one of those to be true. Now, 1 is going to be included because it is included in either here or here. It's included here. What about 6? Do we include that, or are we going to put parentheses at 6? Well, the number 6 is not included in this set, but it is included in this set. 6 is greater than equal to 1, so it's going to be a part of the solution set. And we don't have to mention it when we put our answer into interval notation because there's nothing interesting going on at that point. Okay, so we don't have to mention it. We're just going from 1 to positive infinity, and that is our answer in interval notation. Let's try another. 1 plus 3x is greater than 19, and 4 minus 7x is less than equal to negative 3. Just like the last time, we're going to go ahead and subtract 1 from both sides, then divide by 3. But our word this time is and. I'm going to have a negative 7x less than equal to negative 7. Dividing by negative 7 is going to give me x is greater than equal to positive 1. But let's see what effect the word and has on the inequality. Here I have 1 and 6, my two endpoints in question. And remember, the and means that the numbers included in the answer set have to satisfy this inequality and this inequality at the same time. So let's try numbers in this interval. In this interval, are those numbers greater than 6? Absolutely not, so we're not going to include them. Are these numbers in this interval greater than 6? No. Now they are greater than or equal to 1, but remember, with the and, we have to have this and this true at the same time. When we're looking at something greater than 6 over here, definitely greater than 6, and it's also greater than equal to 1. So we are going to include the numbers in this interval in our set. Now, the question is, do we include the number 6 or not? The real question is the number 6 included in this set and in this set? Is 6 greater than 6? No, it's not. So we cannot include it. It doesn't matter if it works for this one because it has to work for both of them at the same time because of the and. So we're not going to include the 6. We'll write our answer as 6 with the parenthesis and on to infinity. Now let's look at solving absolute value inequalities. In thinking of absolute value as distance from 0, if we have this statement of the absolute value of x must be greater than 5, it follows that x must be more than 5 units away from 0, correct? Let's think of x as the solution that we want to shade. Here is 0, here is 5, and these numbers are more than 5 units away from 0, so they're included in our solution set. But we also have over here -5. The numbers to the left of -5 are also more than 5 units away from 0. So we end up with a solution set of -infinity to -5 union 5 to positive infinity. Now, if the absolute value of x is less than 5, it follows that x must be less than 5 units away from 0. Let's try the same graphing strategy. Here is 0, here is 5, and these numbers are less than 5 units away from 0. But we also have over here -5, and these numbers are less than 5 units away from 0 as well. So we end up with this interval of -5 to 5. Let's solve these absolute value inequalities. First, the absolute value of x is less than 3. Well, I know that if x is less than 3, then the numbers that I would want to shade on the number line are less than 3 units away from 0. X is going to be less than 3, but at the same time greater than -3. When I graph that, we can see from -3 to 3 is shaded to strict inequality, so parentheses on the boundaries, and in interval notation, I have -3 to 3. With absolute value of x greater than 3, I know that the distance that our x is away from 0 must be more than 3. In other words, x must be greater than 3, or x must be less than -3. On the number line, we're thinking of this as x being greater than 3, or to the right of 3, or x being less than -3, or to the left of -3, and we don't include the boundaries. The numbers there on the number line are all going to have a distance of more than 3 away from 0. Okay, so this is just a compound inequality here. We're going to join with a union, -infinity to -3, union 3 to positive infinity. Okay, now just a fun observation and a way to help you to remember what these are going to end up doing. If I have a statement like this, absolute value of x is greater than 5, you notice that the inequality sign is pointing away, out, away from the absolute value. And you notice that we end up with two of these outside intervals that are joined with a union. So it works down here as well. We have, starting out, we have a greater than 3. We're pointing out, away from the absolute value, and I end up with two outside intervals with an OR, and my intervals here joined with a union. On the other hand, if I have this absolute value of x less than 5, we'll always end up with a single inside interval. The arrow, our inequality sign, is pointing in to the absolute value. So it's an inside interval, and we'll have a single inside interval as our answer. So it's a funny way to remember this, but I like to call it the belly button rule. You have innies and you have outies. So this is an outie and this is an innie. And that's a good way to help you to remember, or at least give you a little chuckle that you had to talk about belly buttons in math class. Let's work a couple of similar problems here. Now these are much more involved absolute value inequalities, but our strategy remains the same. We want to isolate the absolute value the same way that we did with equations. So let's go ahead and subtract 1 from both sides here. I'll have 2 times the absolute value of 3x minus 6 is less than 6. This 2 is just a coefficient. It's not part of the absolute value expression, so we need to divide that off. That will give me absolute value of 3x minus 6 is less than 3. Now, I have one of those any expressions where I have the absolute value is less than 3. It's going to be less than 3 away. So somehow this expression is less than 3 but greater than negative 3 in order to keep it within 3 from 0. From here we have a compound inequality to solve. So I'm going to go ahead and add 6 to all 3 parts. That gives me 3 is less than 3x is less than 9. And I'm going to divide by 3. So I get 1 is less than x is less than 3. You can graph this and you'll have between 1 and 3 in your solution set and an interval notation from 1 to 3. Now we have the same absolute value inequality over here, except that we have a greater than equal to. So we start out the same way. We're going to subtract 1 from both sides. We're going to divide by 2. Then we have this absolute value is greater than equal to 3. That means that whatever the statement is inside is more than 3 away from 0. So 3x minus 6 is greater than or equal to 3, or 3x minus 6 is less than equal to negative 3. In other words, we're going to be to the right of 3 or to the left of negative 3 in order to make this expression inside have a value that is more than 3 units away from 0. And then I solve each of these inequalities. So 3x is greater than equal to 9 after I add 6 to both sides. then x is greater than equal to 3 after dividing by 3. I have over here 3x is less than equal to 3 after adding 6 to both sides, and x is less than equal to 1. Remember, we have an or between these. It might be a little more difficult to picture what's going on. So even if the question does not ask for a graph, then it's still a good idea to do it so you can picture what this is and get it into interval notation a little easier. I have x's greater than equal to 3, so we want numbers in this interval, square bracket, or x is less than equal to 1. So numbers over here will work as well. So my answer set becomes negative infinity to 1, union 3 to positive infinity, and we're including the 1 and 3 with square brackets. And one more set of similar problems. Okay, now I want to caution you here. For some reason, students a lot of times will like to take this and distribute it through the absolute value, and you cannot do that. You cannot do that because the absolute value, while it is a grouping symbol, it does not work the same way as parentheses do as a grouping symbol. So we have to do other things to be able to isolate this absolute value. I'm going to go ahead and add 1 to both sides. So I have negative 2 times the absolute value of 3x minus 6 is less than a negative 6 after adding 1 to both sides. Now I need to divide both sides by negative 2. That's how I get the absolute value isolated. When I do that, I get the absolute value of 3x minus 6 is now greater than a 3. Okay, now the absolute value of 3x minus 6 is greater than 3. We're pointing out away from the absolute value, so we're going to have two outside intervals that are joined with an or. I'll have 3x minus 6 is greater than 3, or 3x minus 6 is less than negative 3. These two statements would ensure that this expression here has a value that is more than 3 units away from 0. Now we have two simpler inequalities to solve. I'm going to add 6 to both sides, divide by 3, keep your or as you go down. So 3x is less than 3 here, and x is less than 1. Let's get an interval. Here's 1, here's 3. So x is greater than 3, or x is less than 1. And strict inequalities mean we're going to have parentheses on those boundary points. So my interval notation is going to say negative infinity to 1, union 3 to positive infinity. Now over here, I have to again isolate the absolute value. Do not distribute the negative 2. That's not how it works. So I have a negative 2 times the absolute value of 3x minus 6 is greater than negative 6 after I add 1 to both sides. We get absolute value of 3x minus 6 is now less than 3 because I divided both sides by this negative 2 here. So you have to flip the inequality. Now I have a statement that says the absolute value of 3x minus 6 is less than 3. It has to be within 3 units of the value of 0. So we're going to have this statement of 3x minus 6 is less than 3, but at the same time greater than negative 3, so that the value is between negative 3 and 3 on a distance standpoint. I'm going to add 6 to all three parts, so 3 is less than 3x, which is less than 9, and I'll divide by 3. So 1 is less than x, which is less than 3. And I'm going to graph 1 to 3. X is between those two numbers. And I'm going to use parentheses on the boundaries because of the strict inequalities here. And now in interval notation, I am 1 to 3. So it's at this point in the solving process, once you have the absolute value isolated, that you can decide if you're going to have two outside intervals or a single inside interval, and that will be consistent once you get down here to your answers.